Hey, welcome to Unit 9 Gas Laws. And gas laws are my favorite type of matter. You can't see them, but they can be extremely powerful. Acetylene gas can be used as a torch to cut metal. You use all sorts of gases in welding. We need oxygen to breathe and live. It's also, you can use oxygen to add to a fire to increase the heat of the fire to give it more life. There are all kinds of applications for gases, and when in an ideal form can be easily predicted. So let's get started. Okay, so we're going to talk about some general properties of a gas. Gases are thought of as a fluid because they flow. They take up the size and the shape of their container, and they are easily compressed. When they're not normally in a gaseous state, say water, for example, is usually a liquid. If you put enough energy into water, you can create water vapor, or you can create vapors of other solids even that are normally not in the gaseous state, but if you put enough energy in, you can vaporize them. So if they're not at room temperature, a gas, when they're turned into a gas, they're known as a vapor. There are little to no intermolecular forces between the molecules of a gas. And so we say that the gases don't stick together. They have totally elastic collisions. They act as independent operators. And because of this, under normal conditions, temperature and pressure are things that most affect the gas properties. Okay, so now let's talk about some ideal gas laws. So ideal gases are most predictive when the conditions are moderate. The temperatures are not too high or low, and the pressure is not extremely great. So what happens is that under normal conditions, these gas molecules are free to move and they don't interact with each other a whole lot. When they collide, they bounce off each other and no energy is lost. But if you compress a gas and cool it off, the molecules move extremely slow and they're closer together because you're compressing it, and they stick together. They're a little bit sticky, and so they are not as easily predictable in terms of their properties. But under normal conditions, these gases follow very predictable patterns of behavior that can be predicted by these ideal gas laws. So here again, collisions between the particles are said to be elastic, meaning no energy is lost. The distance between the particles is great compared to the size of the particles under these conditions. All right, and so the size of the gas molecules are so very small compared to the distance. Even if you have a mixture of large and small gas particles, they behave pretty much the same, and you don't have to take into account the size of the molecules when you're working the problems. Avogadro's law: equal volumes of any two gases at the same temperature and pressure contain the same number of molecules. At standard temperature and pressure, 1 mole of any gas contains 22.4 liters of the gas. And so under standard temperature and pressures, we can work stoichiometric problems with these by changing the quantities that we have into moles of the gas. And when we have moles of the gas under these conditions, we can change it into a volume. And the standard temperature and pressure is 0 degrees C and 1 atmospheric pressure. We'll talk more about exactly what pressure means in the following set of slides. Okay, so now we are going to do some problems using Avogadro's law, some stoichiometric problems, and you will find that these are very similar to the stoichiometric problems that we did before. And so let's start with a flow chart here. We'll have grams to moles, just like we did in the previous units, and we'll use the molar mass off the periodic table to make that conversion. And then we're going to go from moles of one chemical to moles of the other, just like before. And then we're going to use the coefficients off the balance equation, just like before. to change from one chemical to the other using that balanced equation. And then instead of going from moles to grams again, we'll go from moles to liters here using 22.4 liters is equal to 1 mole. And that is under standard temperature and pressure conditions. Alright, so in this particular problem we're given 500 grams of pentane and we're asked to solve for liters of CO2. Liters of CO2. Alright, so we're going to go from grams to moles, then we're going to go from moles to moles, and then finally moles up here to liters. So we'll have 3 steps, just like our grams to grams type of problem, but the last step will be a little bit different here. Okay, so let's write down our 500 grams. Always write down the given. If you can't do anything else, you can write that down, right? C5H12. And we know that we have to get it into a mole amount to change 2 moles of carbon dioxide. So here we'll have we'll have grams of C5H12 for every 1 mole of the same. And to save ourselves some time, I went ahead and calculated the molar mass of C5H12, and that is going to be 72 grams. Alright, so maybe we'll go ahead and do that on this first one. C5 times 12 is equal to 60, right? And then we have H12. 12 times 1 is equal to 12. So that gives us 72 grams per mole for that guy. So now we're at moles right here, and we'll need to go to moles of the different chemical. So we have to go over our mole bridge here. So we'll have moles of pentane on the bottom. Remember, whatever you have on the top has to go on the bottom so it'll cancel out. Our grams have already canceled out. And then we'll have, for C5H12, we just have 1 mole because there's no coefficient in front of the chemical symbols there. And then to solve for, we're going to go to carbon dioxide, so we have 5 moles of carbon dioxide. And then our final step here, we're going to go from moles to liters. So since we have moles on the top, we'll say every 1 mole of CO2, we've got 22.4 liters of carbon dioxide. So moles of CO2 will cancel, and our final answer will be in moles. I'm sorry, excuse me, liters. I'm getting excited there. Liters of CO2. So if you multiply across the top, 500 times 5 times 22.4, and then divide that by 72, you should get 777.8 liters of CO2. We've got 4 significant figures at our starting place, so we'll get 4 in our answer. All right, so now your turn. Pause the video, work that problem, and see how you come. Alrighty. Alright, hopefully you've done that. So now we're starting with 500 grams of high quality H2O. So in this problem, we're starting with 500 grams of this guy, of the product, and we're asked how many liters of oxygen are needed for that. So let's do this one. Work it backwards. Why? Because it's so much fun. 500 grams of H2O. Okay, so we're going to have to get to moles. Remember, you always have to get to moles to change chemical species. So I've done that one for us. It's 18 grams per mole for water. And then we'll go over our mole bridge, changing chemical species. We'll have moles of water on the bottom. And here we have 6 moles of water. And then we'll have moles of oxygen on top, because that's what we're solving for. We're eventually going to get to liters there. We've got to go to moles first. Have 8 moles. You've got to crawl before you can walk, right? And then finally, our last step here will be moles to liters. For every 1 mole of O2 at standard temperature and pressure, STP, we have 22.4 liters of O2. And if you do that one, you get 829.6 liters of oxygen. Alrighty. Alright. So that concludes recording 1. You may be asking yourself, well, what if I don't have standard temperature pressure? How do I predict the amount of volume that I can produce? Well, we will do that in the following slides and talk more about some other gas laws besides Avogadro's law. And so, fun. I think you'll enjoy these units on gases. Just a neat way of connecting math to concepts.